Species are on the move. Species around the globe have been observed shifting their distributions deeper into the oceans, upwards in elevation on land, and generally toward the poles. This global reorganization of biodiversity is one of the large human impacts on the planet. This map is showing where range shifts have been documented in the oceans. The shrunken regions are relatively data poor, and the color of each grid cell shows the degree to which those range shifts were consistent with climate velocity, the direction we predict them to shift based on climate change, which is usually toward the poles. So you can see that this map is overwhelmingly blue and species in the oceans are largely tracking temperature change. But it's one thing to attribute range shifts to a driver and quite another thing to make predictions based on that driver. In ecology, our ultimate goal is often prediction. Sometimes this means predicting the past in order to test whether the models that we've developed have skill in understanding ecological dynamics. But increasingly, we're trying to forecast the future to make predictions that people might actually use for everything from tourism development to urban planning and natural resource management. If we could make those predictions based only on temperature, this would be a much shorter talk. But unfortunately, we are not that lucky. This is a figure from some of my previous work on the dynamics of range edges under climate change from around the oceans. The x-axis shows where the edge shifted over time. Each dot is a different range edge. And if it's to the right of this zero line, a positive value, that means it shifted toward the poles, which is the direction that we'd expect based on warming. If it's to the left, it shifted toward the equator. But what I want you to focus on is actually the y-axis, which shows how much the temperature experienced at that range edge changed over time. If these edges were all perfectly tracking temperature, either summer temperature or winter or both, those dots would fall entirely on this zero horizontal line. You can see a lot of them are clustered there. There is a strong relationship between edge position and temperature, but there's also a huge amount of variation. This relationship might be sufficient for some purposes, depending on what you're trying to predict. But for a lot of goals in natural resource management and conservation, we need more accurate and precise forecasts of species on the move than you could generate based on environmental correlations like the one I'm showing you here. The way forward that's been proposed is process-based modeling, where we explicitly link the outcome we're interested in. In my case, it's usually the distribution and abundance of species with some drivers through a mechanistic process. This figure is showing what some of those prevalent processes could and should be that we can model. The work I'll present incorporates dispersal, demography, physiology, and spatial gradients over the environment. It doesn't yet incorporate species interactions or evolution, although hopefully you'll see that those could easily be added in the future. The specific class of models that I've been working on are called dynamic range models, and this slide will walk you through how these work. It's a class of species distribution model that starts the way other species distribution models start, with data on the distribution and abundance of species. But then we write down a model that describes mechanistically what we think is driving the distribution and abundance. It might have processes in it like growth, reproduction, dispersal, migration. Some of those processes might vary over space or with temperature. Once we have that process model in hand, we can fit it to these data and estimate the key parameters of the model. Again, those are often things like growth or dispersal. You probably see where I'm going with this. Once we have the structure of this process-based model and our parameter estimates, we can simulate the future or simulate any period without the data, just running forward the process model that we wrote down and the parameters that we estimated to get back occurrence and abundance, which is what we started with and what we are interested in modeling. So these models have a lot of promise. The parameter estimates themselves can be very interesting from an ecological standpoint. They can also potentially do a better job than other strategies of capturing transient population dynamics because at their core, they're demographic models that incorporate and deal with the relationship between abundance and distribution. They, for all these reasons, might be able to project into no analog climates, which is to say that because they have these functional relationships between the environment and vital rates in a model, they might do better at projecting into environments that an organism has never experienced in the past than a correlative model, which is really tied to historical data on the environments the organism did experience. So for all these reasons, these could be extremely useful for short-term forecasting. But there are lots of reasons why they haven't been more widely implemented. They're extremely data hungry. The parameter estimation process can be really difficult. And in particular, it's a challenge to identify at which scale every process should be modeled. How much do you downscale something like reproduction through a landscape? How large do you make your estimate of different populations? Those are model choices that really affect the outcome and can be quite difficult to figure out. And for all these reasons, dynamic range models have really only been demonstrated on simulated data. So our goal was to field test them on real data and evaluate their ability to provide useful short-term forecasts for marine species on the move. I'm not going to show you the equations for this model, but I will show you instead a Bayesian network diagram of one of the process-based models that we're testing against real data. So the quantity that we're trying to estimate is at the center of the slide, the true population size for every patch. This is a patch structured model. That's how we incorporate space. Every age, it's an age structured model, and every year, which is our time step. And here we're saying that that true population size is conditional on a number of variables related to recruitment. In the oceans, recruitment can be a very stochastic process. So we're modeling that here. And all of these dark boxes at the bottom are parameter estimates in the model. So this one at the bottom is related to that stochastic recruitment. And then we also have temperature affecting recruitment. So we're estimating an optimal temperature and its sensitivity, recruitment sensitivity to temperature. In addition, we're estimating process error and a rate of dispersal among these patches. And we pass the model data on actual temperature, that's over here to the right, and a mortality rate from the literature. This alone might be somewhat of a challenge to estimate, but it's actually only half of our challenge because the data that we have weren't collected perfectly. In particular, because these data are from fishing surveys, they catch large fish in the net much more frequently than they catch small fish. So wrapped around this process model, we have an observer model that estimates the true population size based on what we observe, which is here in blue, all of the processes we just mentioned, and some additional parameters related to the sampling process, like observation error, and a couple more parameters that capture the difficulty of catching small fish and the probability of encountering fish at all. This probably sounds like a very theoretical project so far, and it is, but it's also a collaboration with fisheries managers using fisheries data. All of the data come from the National Oceanic and Atmospheric Administration surveys that are conducted off of the Northeast United States every year. And we've grouped those into the patches that you see in the map on the left. With our partners at the Mid-Atlantic Fishery Management Council, we've identified 4 focal species that we're field testing the model on that have various important roles in commercial and recreational fisheries. We're fitting the model to data from 1972 to 2005, and then forecasting it for the final 10 years of data from 2006 to 2015. So that's our out of sample forecast. We hide the data from the model, run it forward with our parameter estimates, and ask, did it do a good job of forecasting short-term distribution and abundance changes? All of the plots I'm going to show you from now on are for summer flounder, which is the first species we've started with. This is what has actually happened to the species over space and time. On the x-axis is the year, and the y-axis is the patch, which you can see numbered on the map. There are a few key features of what this population has done that I want you to notice. The first is overfishing. In the middle of this time series, which is the 80s and 90s, the bright colors all go away. The bright colors are the highly abundant patches, so you can see that the population just collapses. The second feature is that it does recover really strongly late in the training time series, which is what we're looking at, but it recovers much further north than where it started. So we have a number of dynamics that the model fitted to the data needs to capture: the overfishing induced collapse, the recovery, and the northward shift. Here's what our model estimates. Now, this is when it is fitted to the data, but we still want to be sure that its true estimate of population size is a sane one. And you can see here, it does capture all of those important features. Now we're looking at the model estimate of true population size over space and time. And you see the overfishing effect where there's a huge decline in abundance in the middle of the time series. You see the recovery and you see the northward shift. One way to summarize those shifts is by looking at the centroid, which is the weighted range center, weighted by biomass. The red dots here show the actual data, and the blue is what the model thinks the true population size was. This is a sanity check for us. The model recaptures the core dynamics of the population that we observed. And you can see it actually does a good job with these small ups and downs when fitted to the data. But the real test is when we hide the data and only forecast the most recent decade and then test whether the model accurately recovered with the parameter estimates from this fitting process what actually happened. So let's look at those plots. This is what the model thinks happened in the final testing decade. What it's saying is that the species continued to shift north and got much more abundant more recently in that decade. On the bottom left, you can see the same plot for the true data, what actually happened. And that is indeed the pattern that we're trying to recreate. So you see an increase in abundance over the time series and a continued shift north, especially in this patch 6 in the far northern patches, which the model accurately forecasts with our process-based equations. And this is the centroid picture. Again, now we're testing out of sample, and the model is actually capturing these small ups and downs from year to year when the species shifted north and south and north again. It's able to identify those short-term range dynamics from our dynamic range modeling approach. So we're very excited about these results, but we have a lot of work left to do. We're fitting different process-based models to the data. What I showed you is just one, the temperature-dependent recruitment model. We're also comparing this to other modeling approaches that are correlative in nature to test which ones do the best job of capturing features like centroid shifts and range edge shifts. And we're expanding this to a lot of other species to hopefully develop a body of examples for when empirical field-tested process-based models can actually forecast species on the move. Thank you so much for your attention.